Hello, this is FlippedHarber for Physics, and in this video we're going to go over the practice problems on page 97, numbers 15 through 18. In number 15, you place a watermelon on a spring scale at the supermarket. If the mass of the watermelon is 4 kilograms, what is the reading on the scale? Now, I've drawn a free body diagram on the watermelon here, and there's really only two forces acting on the watermelon. There's its weight, that is the downward pull from gravity, which is equal to mass times gravity. The mass of the watermelon times 9.80. Pretty safe assumption this supermarket's on Earth. The only other force acting on this watermelon is the normal force. Now, what is providing that normal force? Well, it's the scale that the watermelon is sitting on. So the scale is actually reading the force that it has to exert on the watermelon in order to counteract gravity. So if I do a sum of forces, I'm going to set that sum of forces equal to 0 because the watermelon is not accelerating. Solving for F sub n, we just get mg. That is, that the normal force is equal to the weight of the watermelon. So I plug in my mass of 4, I plug in the acceleration for gravity, 9.80 here on Earth, and I find out that there is a normal force of 39 newtons acting on this watermelon. So that's what the reading on the scale should be. Alright, let's move along. Kamaria is learning to ice skate. She wants her mother to pull her along so that she has an acceleration of 0.80 meters per second squared. I know, kids are asking for that all the time. If Kamaria's mass is 27.2 kilograms, with what net force does her mother need to pull her? Neglect any resistance between the ice and Kamaria's skates. So, I have a picture of Kamaria here, or at least a reasonable facsimile thereof. Now, there's a couple extra forces I haven't drawn in here, specifically Kamaria's weight and the normal force. But I'm not worried about those. Those act in a totally different direction. The only force I'm actually worried about is anything that happens with or against Kamaria's mother's pull. Now, since we're neglecting any resistance between the ice and Kamaria's skates, that's the only force I need to worry about, is the pull from Kamaria's mother. So, that force is equal to mass times acceleration. I'm just applying Newton's second law here. Plug in the mass and the acceleration, and we find out that her mother is pulling with a force of 22 newtons. Alright, in number 17, Taru and Reiko simultaneously grab a 0.75 kilogram piece of rope and begin tugging on it in opposite directions. If Taru pulls with a force of 16 newtons and the rope accelerates away from her at 1.25 meters per second squared, with what force is Reiko pulling? Well, we're going to do a sum of forces and set it equal to ma. We know that Taru is pulling with a force of 16 newtons. Now, I've pointed that in the opposite direction, so I'm making that the negative force of the two. I'm going to solve for the force from Reiko, and I'm going to let that one be the positive. I plug in my mass of the rope, I plug in my acceleration of the rope, do a little bit of multiplication and moving stuff around, and we find out that Reiko's force is 16.9 newtons. Not a lot bigger than Taru's force, but the acceleration isn't that much either, so I shouldn't be surprised that it's not a lot bigger. Alright, number 18. In figure 4.8, the block has a mass of 1.2 kilograms and the sphere has a mass of 3 kilograms. What are the readings on the two scales? Now, I'm going to take a logical approach to this rather than a really hardcore Newton's second law method to this. I want to talk about the job that each scale has. Okay, so the weight of the block, I'm just going to take the 1.2 kilograms multiplied by gravity. The weight of the sphere, take its mass multiplied by 9.80. Okay, finding the weight of these two objects is not a big deal. Let's talk about the top scale. The top scale is responsible for holding up both the block and the sphere. So in order to find out what the top scale should read, I add up the two weights. The weight of the block plus the weight of the sphere is 41 newtons. Now the bottom scale only has to hold up the sphere. It doesn't have to hold up the block. So the reading on that is only equal to the weight of the sphere, 29 newtons. Alright, so that's it for those practice problems. Time for you to try some of them on your own. I'll see you in class, and I'll see you online.